Good morning, everyone. Let's start the second day of PKC. First up, we have Rune talking about the security analysis of Signal's PQXDH handshake.
Thank you. Is the microphone on? Can you? Yeah. Okay. Good morning. My name is Rune Fiedler, and this is joint work with Felix Günther. So let's first look at the setting of Signal. And oh wait, do I have to switch this on? Yes, I have to switch it on. Yes, let's look at the setting of Signal. We have Alice who wants to talk to Bob, but Bob is a very late sleeper and still asleep at 9 a.m. So how do they do this? What they do is they travel back in time to yesterday evening, and then Bob computes a pre-key bundle, which he uploads to the key server on the first arrow here, this one. Then Alice, when she wants to start the conversation this morning, she queries the key server for Bob's pre-key bundle, who promptly returns it. This allows Alice to start the conversation, send over her own public keys to Bob, even if Bob is offline. This is the asynchronous part of the key exchange. Furthermore, we want it to be authenticated, in the sense of Alice should be sure that she is talking to Bob, and vice versa. And we will be talking in the next 20 minutes about this part here, the initial handshake, up until both parties agree on a shared session key. And they can converse afterwards as well, but we're not going to talk about this in this talk. So let's have a look at the initial handshake protocol that Signal is using. So far they have used X3DH extended triple Diffie-Hellman, which they have recently upgraded to PQXDH post-quantum extended Diffie-Hellman. So let's start with the first one, the classical, and then we'll get to the post-quantum extension. So what you see here is lots of Diffie-Hellman key pairs. Both Alice and Bob have a long-term key pair and an ephemeral key pair. Ephemeral in the sense of they use it only once. Bob additionally has a semi-static key pair, which he rotates, say, once a month. Bob signs his semi-static public key under his long-term key. Then Bob sends over his public keys and the signature on the semi-static key to the key server, who forwards it to Alice. Now Alice has all the public keys and her own keys that she needs to compute several Diffie-Hellman combinations. That is, she pairs her own long-term key with Bob's semi-static key and her ephemeral key with each of Bob's public keys, resulting in 4 Diffie-Hellman shared secrets. And she uses these 4 Diffie-Hellman shared secrets to derive the session key. She sends then her own public key over to Bob, who can derive the same session key from this. Right. Then the extension to PQXDH is that we add a chem on top of it. In particular, Bob now has an ephemeral chem key on top of it, which he signs under his long-term key as well. Both the ephemeral chem public key as well as the signature on the chem key are part of the pre-key bundle. Alice now encapsulates against Bob's chem key and includes the chem shared secret into the key derivation, and she of course also includes the chem ciphertext into her message to Bob, so that Bob can decapsulate the ciphertext to derive the same shared secret and the same session key. Now you might remember I said that ephemeral keys are used only once, and Bob uploads pre-key bundles to the key server, so it may happen that the ephemeral keys are exhausted, and there's just no more ephemeral keys. In that case, we have a reduced session without any ephemeral contribution from Bob. So no ephemeral Diffie-Hellman key from Bob, and no ephemeral chem key from Bob. Instead, Bob will use a semi-static chem key, which is also signed. Okay. Now that we're familiar with the protocol, let's have a look at the state of research on this. And what we have seen so far is a reductionist analysis from Cohn-Gordon et al. In 2017 of the original classical X3DH protocol in a Bellato-Rogoway-style key exchange model. Furthermore, for PQXDH, we have recently seen a tool-based analysis by Bhagavan et al. In CryptoVerif and ProVerif in the computational and symbolic model, respectively. They have rediscovered a potential chem re-encapsulation attack following Kremers et al. However, their analysis has some downsides. One is they only cover the compromise of long-term keys and not of semi-static or ephemeral keys. and they only look at the reduced mode of the protocol, so the mode where Bob has no ephemeral contribution. This is complemented by our work, which follows the Bellato-Roggeway style key exchange models of Con-Gordon et al., which was later refined by Brendel et al. And we additionally improved the model by explicitly modeling the signatures on the keys. So previous models have just assumed that semi-static keys are authentically delivered. We do not assume that. We model the signatures on the semi-static keys to capture this. Furthermore, our analysis identifies the precise requirements of the CAM that we need to prevent the CAM re-encapsulation attack. And we model the maximum exposure guarantees that Signal strives for with a couple of clean predicates. Maximum exposure means that, you remember from the previous slide, we have 5 shared secrets, 4 Diffie-Hellman shared secrets, and a CAM shared secret from which we derive the session key. And as long as at least one of them is not known to the adversary, the session key should remain secure. This is the maximum exposure security, because the maximum of everything else can be exposed. And we model this with clean predicates in the sense of, for each contribution, one of them has to be clean, and then we're good. This will get hopefully clearer in the next slide, where we will see the concrete bound that we have derived for PQXDH against classical adversaries. I understand this may look slightly intimidating or frightening, especially this early in the morning, but I hope it will look less frightening by the end of this talk, because we will walk through it bit by bit. So first, in the top line, we have a couple of correctness terms, like precluding correctness errors in the CAM decapsulation, keys not colliding, that type of thing. And then we have a big case distinction here, depending on which clean predicate holds. So for example, in the first line, this is the cleanness of the Alice's long-term key combined with Bob's semi-static key. If that case holds, we get this bound here. And we get slightly different bounds for the other terms, depending on which pairs of contributions are not corrupted by the adversary. Next, I would like to draw your attention to this term here, the leak plus R term, because this is the term that prevents the CAM re-encapsulation attack. And before I keep talking about the CAM re-encapsulation attack without you knowing what it is, let's walk through it. The setting is as follows. We have 2 sessions between Alice and Bob. Both of these sessions are reduced sessions, meaning there is no ephemeral contribution from Bob. Furthermore, both of these sessions have the same Diffie-Hellman keys all over. But Bob uses different CAM keys in both sessions. So what happens is that Alice now in the first session sends over her message to Bob, which includes a CAM ciphertext. Now the adversary compromises Bob to learn the CAM secret key. With the CAM secret key, he can decapsulate the CAM ciphertext to learn the encapsulated CAM shared secret. And with this CAM shared secret, he can re-encapsulate it to a different public key. Wait, what? Re-encapsulating a CAM shared secret? What is that supposed to look like? So let's have a look at a naive CAM construction, which randomly samples a shared secret and encrypts that under a PKE scheme. And if this is what the CAM looks like, then you can see, just take the shared secret from here, encrypt it under the PKE scheme under a different public key, and you get a CAM ciphertext for a different public key, which encrypts the same CAM shared secret. This is what the adversary can do, even though we do not expect it to happen. This is what the adversary does here, and includes the modified ciphertext into the second session. Okay, now remember, the session key is derived from the 4 Diffie-Hellman shared secrets and the CAM shared secret. Because the Diffie-Hellman public keys are the same in both sessions, the Diffie-Hellman shared secrets are all the same in both sessions. And due to the CAM re-encapsulation, the CAM shared secret is the same in both sessions as well. Meaning both sessions derive the same session key, even though they are not partnered. These are clearly different sessions. So what happens is the adversary can reveal one session and test the other, thereby trivially winning the game. One easy way to prevent this with a fix at the protocol level would be to include the CAM public key and CAM ciphertext in the key derivation over here, because then both of these sessions would derive different session keys, and the adversary could not do this simple strategy. However, we are not trying to fix the protocol, we're trying to analyze PQXDH as is, so we need to figure out what is the property that we need of the CAM to prevent this type of attack. And we need a type of binding property here, which was introduced by Kremers et al. And there's a couple of them, and I'll contextualize this in a minute. The security game looks as follows. First, the challenger samples a couple of chem key pairs and gives the full key pair, including the keygen randomness, to the adversary. Then the adversary outputs two public keys and ciphertexts, which are distinct. But both of these ciphertexts have to decapsulate to the same shared secret. If this is the case, then the adversary wins. So this is what we do not want to happen. So what this intuitively does is the shared secret binds the public key and the ciphertext, hence the name of the notion. The prefix leak plus R denotes the adversarial power here, because what the adversary here gets is the full key pair. It gets leaked the full key pair plus the keygen randomness. This is in contrast to different adversarial models from Kremers et al. One being the leak setting, where the adversary gets the full key pair without the keygen randomness, and the malicious setting, where the adversary can choose the public key itself. We show implications from top to bottom and separations from bottom to top, where MLChem is a noteworthy separation example between our leak plus R notion and the malicious notion. What we need for our analysis is leak plus R. Signal uses Kyber, which we show fulfills our leak plus R notion. Similarly, MLChem also fulfills our notion. On a side note, the tool-based analysis by Bhagavan et al. Uses a different notion, which is formally incomparable to ours. Okay, coming back to our security bound, I would like to highlight a different term here in blue, and this is the hybrid combiner bound that we get. So let's look at the case where the ephemeral contribution is clean. Then we have Diffie-Hellman 4 is what we rely on for security, and the chem shared secret. So in order for the adversary to win in this case, it needs to break both gap Diffie-Hellman and one-way CCA. This is why we get this minimum term of both of these advantages here. And then there is one more special case that I want to mention, which is the final case. This is a case that PQXDH has, which X3DH does not have. So it's an additional security guarantee that we get against an adversary that is now active and later gets a quantum computer. And we get this guarantee due to the ephemera chem key being signed. Because since the ephemera chem key is signed, the adversary cannot modify or substitute the chem key now. And since the chem is quantum secure, even a future quantum computer does not help the adversary to win against this case. Okay, this is our bound for the classical adversary, and I hope it looks less frightening now. And we have a similar but simpler bound for quantum adversaries, because for quantum adversaries, we cannot at all rely on Diffie-Hellman guarantees. So all we get is security from the chem, which is just in case of we only have one chem, so we have two cases because the chem might be ephemeral or semi-static in the reduced case. Note here that we use int CCA here instead of one-way CCA, but this allows us to give a proof in the standard model, while the classical proof is in the random oracle model. Which brings me to a design decision of PQXDH, and the foremost goal of PQXDH is to give a hybrid guarantee that protects against quantum adversaries. And for that, PQXDH adds a chem shared secret into the key derivation, which is a very good measure to achieve this. Furthermore, PQXDH overshoots its own security goals by protecting against active now quantum later computers by signing the ephemera chem key. Another solid thing. However, there's room for improvement. For one, it would be a good idea to add the session context to the key derivation. In particular, to add the chem public key and chem ciphertext here. This would allow us to forego the binding requirement on the chem and also allow for a tighter proof. Lastly, the signatures on all of these public keys, it would be nice to have them domain separated, because otherwise you can have some key confusion between Diffie-Hellman and chem keys and between chem ephemeral and chem semi-static keys. Right now, our model specifically excludes them to get the proof to go through, but it would be nice if we wouldn't need that, and it's easy enough to add this domain separation. With this, I would like to conclude. In the last minutes, we have first looked at PQXDH, which is an extension of X3DH and adds a CAM on top of the classical protocol. For the scheme to be secure, we need the CAM to fulfill our leak plus our binding notion, which we separate from the malicious and the leak notion. Furthermore, we show that both Kyber and MLCAM achieve this notion. Signal, who's currently using Kyber, is therefore safe. If you don't want the CAM binding assumption, then you can just include the session context in your key derivation. Next, we have looked at the security bound for classical adversaries down here. In particular, we have paid attention to the leak term here, which prevents the CAM re-encapsulation attack, to the hybrid combiner bound, and to the extra case, which prevents active now quantum lecture attackers. And finally, we have looked at the bound for quantum adversaries. And I would like to end on a personal note. I'm hoping to defend my PhD this summer, and I'm looking for a research-oriented job afterwards in secure messaging, in academia or industry. With that, I'm happy to take questions.
Thank you, Rune. Are there any questions from the audience?
I'm wondering why you didn't use in the CCA for the classical setting.
So we get away with the weaker one-way CCA assumption because we do not need to figure out where we need to embed the challenge. So we have the gap Diffie-Hellman, which in the first, so here in these two cases, we use the gap Diffie-Hellman to figure out where to embed the challenge. And then we can use the the one-way assumption. However, here for the quantum case, we do not know where to embed the challenge, so we need in CCA here.
So it's possible to prove the security within the CCA?
Yes, but one-way CCA is a weaker assumption.
Yeah, I know, but yeah.
Okay.
Yeah, thank you very much.
Yeah, if you want, we can talk about this in more detail after the session.
I actually also had a question on this.
Sure.
So in this last term, why do you need to guess the random oracle query?
This is more or less the same question in disguise. Because here we can use the DDH oracle of the gap Diffie-Hellman assumption to figure out where to embed the challenge. However, here, in this case, we're only relying on the CAM and not on any gap Diffie-Hellman. So we do not have the DDH assumption, and therefore we need to guess the random oracle query which relates to the challenge.
And something like one-way PCA wouldn't help?
This sounds like an even weaker assumption than one-way CCA.
That's why I'm surprised.
This may or may not work. I cannot say for sure, but I'm happy to check this offline.
Any other questions? I'm also wondering, why Signal did not do this, or whether they would have incentive to include the context?
I guess they didn't think of it at first. As far as, well, I guess once they want to do a breaking protocol change, then it would make sense to include it anyway. But yeah, since this would break, this is not something you do lightly.
Okay, more questions? If not, let's thank the speaker again. Before we move to the next talk, there are some free seats on this side, or I would encourage people to move a little bit inside to make space. Our next talk is about non-interactive key exchange, new notions, new constructions, and forward security by Roman.
Okay, thank you for the introduction. So this is a joint work with Shufradip and Dennis. And in this work, we introduce a new, more powerful notion of identity-based non-interactive key exchange. But before I go into that, I want to recall the existing notion of identity-based non-interactive key exchange. So an identity-based non-interactive key exchange, for short ID Nike, we have a trusted central key generator where every user can go, prove who they are, and then they receive a user secret key for their identity. The identity can be anything that uniquely identifies a user, like an email address. And when the two users, Alice and Bob, have done that, they can use their user secret key together with just the identity of the other user to derive a shared key. And when Alice and Bob do this, they should get the same shared key. And a security notion, we want that an adversary who has Oracle access to user secret keys and shared keys should, for one challenge pair that he picks, should not be able to distinguish between a real or a random shared key. Of course, as long as that's not trivially revealed to the adversary. So this is very similar to identity-based encryption, if you have attended yesterday's session, just that you get a key exchange functionality instead of encryption functionality. In the talk, I will sometimes also refer to public key Nike. That's basically the same functionality, but with a different key infrastructure, namely the traditional key infrastructure where everybody generates its own public secret key pair. Okay, so back to identity-based Nike. The state-of-the-art constructions are a construction based on pairings in the random oracle model, and in the standard model we currently only know how to build this from strong assumptions such as indistinguishability obfuscation. There's also a hierarchical variant of identity-based Nike that's very similar to hierarchical identity-based encryption, where we have identities, or the identities are organized in a tree structure, and every user can generate a user secret key for its children. Okay, so with the existing notion of identity-based Nike, we have the following problem. So imagine we have two companies, company A and company B, and for their internal communication, they use an identity-based Nike scheme. But of course, for their internal communication, they don't want to trust anyone outside of that company. So each company uses their own key generator. So maybe that's some manager of that company. And that key generator can generate a user secret key for every employee of the company. Then within each company, the employee can derive a common shared key and use that for encryption and authentication and these things. But now imagine that some employee of company A wants to talk to an employee of company B, maybe to negotiate a contract. And for that, they are willing to trust both of their key generators. However, with identity-based Nike, they cannot do this, because at least not without any additional interaction. Because there's no way that two users can derive a shared key when they use different key generators. And note here that such a problem would not exist if these companies would use identity-based encryption instead of identity-based Nike. Because for IBE, everybody can generate a ciphertext for someone else. You just need to know the master public key of their key generator and the identity. And another problem that essentially is the same problem is the following. So for identity-based encryption, we have several results that help us to build regular public key encryption. So for example, by Canetti, Halevi, and Katz, there's this result that identity-based encryption implies in CCA secure public key encryption with one-time signatures. And another result by the same authors in a different work is that the hierarchical version can be used to build forward secure public key encryption. And yeah, it would be interesting if we could get the same results in the Nike setting. However, we currently don't know if identity-based Nike implies dishonest key registration secure Nike, where dishonest key registration security is basically the Nike analog of in CCA security. So this would be an analogous result, but we don't know if that holds. Likewise, we don't know if hierarchical identity-based Nike can be used to build forward secure Nike. And the technical problem that appears here is maybe surprising, that because identity-based encryption trivially implies public key encryption, but currently we don't even know if identity-based Nike implies normal public key Nike. And that's the main obstacle here. So in our work, we now introduce a new notion that we call multi-authority identity-based Nike, and add an H for the hierarchical variant. And it basically solves exactly the problem that I presented with the two companies before. So now we can have two users that use different key generators to derive their user secret key. And additionally, we asked each key generator to issue a master public key. And then two users can derive a common shared key using their own user secret key, the master public key of the other user's key generator, and the identity of the other user. And yeah, with this, I hope it's very obvious that the company example I presented before is solved. So what about these other examples that I just showed you? And here we obtain also positive results in our work. So we show that this new multi-authority identity-based Nike notion actually implies int DKR secure Nike. And it's even a bit simpler because we don't even need one-time signatures. And also the hierarchical variant can be used to build forward secure Nike. And the reason why this suddenly works is basically that multi-authority ID Nike trivially implies Nike. And it also implies identity-based encryption, which both imply public key encryption. Okay, so what about instantiations? So we show in our work several instantiations of this new multi-authority ID Nike based on existing constructions of ID Nike. And probably most practical, or the only practical construction of identity-based Nike is the SOK ID Nike by Sakai, Ogishi, and Kashara. And it's, by the way, one of the first constructions that used pairings in cryptography. And it's very similar to the Boone-Franklin IBE, if you know that. So it works as follows. The master secret key here is a random exponent alpha. User secret keys are, for an identity ID, are computed as follows. You hash the identity and take it to the power of alpha. And this hash function will be modeled as a random oracle. And the shared key for two users is now the pairing applied to both hashed identities taken to the power of alpha. And you can compute this, or both users can compute this by pairing their user secret key with the hashed identity of the other user. So it can be shown that this is secure under the bilinear decisional Diffie-Hellman assumption in the random oracle model. For the multi-authority version, we need trilinear maps instead, so that's a much stronger assumption. And it works as follows. So the master secret key and the user secret keys are the same. As additional master public key, we now have G to the alpha or G to the beta for the other key generator in this example. And the shared key is now the trilinear map applied to both hashed identities and the generator taken to the power of alpha times beta, where alpha and beta are the master secret keys of the two key generators. And both users can compute this by putting into their trilinear map their own user secret key, the master public key of the other key authority, and the hashed identity of the other user. And yeah, it's basically has the same security properties, except that you now need trilinear maps instead of pairings. And with a multilinear map, we can also get a multi-party version of this, so where not just pairs of users, but bigger groups of users can derive a common shared key. And with leveled multilinear maps, we can get a hierarchical version. However, that's only selectively secure. Then we also take a look at the Bundesentry identity-based Nike, which is a Nike based on an ID Nike based on I/O, and we show that this construction can also be adapted to the multi-authority setting, and for that we need I/O, IBE, and a perfectly binding commitment. And when we replace IBE with an HIBE, we get also a hierarchical variant. And as before, this is only selectively secure. And finally, we adapt the work by Hofheinz et al. That construct identity-based Nike based on universal samplers. So our construction now needs universal samplers and IBE to build ID Nike and multi-authority ID Nike. And universal samplers are a very powerful tool that we currently only know from I/O and the random oracle model. And again, we can get a hierarchical version if we use HIB instead of IBE. And here the advantage is that we get adaptive security. And yeah, of course, you might have noticed that we need now very heavy assumption for our multi-authority ID Nike. However, these heavy assumptions are also needed at least for the hierarchical version of the traditional ID Nike notion. So in fact, in terms of assumption, it looks like constructing an L-level multi-authority HID Nike is about as hard as constructing an L+1 level identity-based Nike. But this is just an observation in terms of the assumption we need. We don't know how to prove any of the implications suggested here, and I think it's quite difficult to show such an implication or such an equivalence. Okay, so finally I want to talk about forward security, which is one of the applications of our new notion. And for forward security means that we use a different shared key for each time slot. And the idea here is that an adversary who breaks in one time slot can of course corrupt the current time slot and also all future time slots, at least when you don't have any interaction or if the adversary is active. And the goal of forward security is to protect all previous time slots. So to achieve this, we need some non-interactive key update mechanism so that when we have a secret key for time slot t, we can compute a secret key for time slot t+1, but of course the reverse should be difficult to achieve forward security. And this is very similar to the key delegation in hierarchical IBE or ID Nike. And that was, I think, also the reason why Canetti, Halevi, and Katz discovered the following very elegant construction of forward secure public key encryption from HIBE. So the idea is that you use a binary identity tree, and each node in that tree corresponds to one time slot, and the order is the pre-order traversal of that tree. So initially you will use the root key of that tree for the first time slot, and then if you want to update to the next time slot, you use the delegation mechanism to compute now in this example the keys for the time slots 2 and 5, and you delete the root key. Note that this operation cannot be undone. And yeah, similar to update. So here in this example now, the user will store the keys for slots 2 and 5, but of course only use the key for slot 2 because we are now in the second time slot. To update to time slot 3, we will do the same, just with the key for time slot 2. So we will delegate it to both children and delete it. And when we hit the leave node and we want to update, we just delete that node. So for 3, we can delete it and just start using the key for time slot 4. Next update again, we will just delete that node and start using the one for 5. And here we have to again delegate once, and yeah, I hope you get the idea. And yeah, this construction only needs as total key size the logarithm of the number of time slots. So in particular, you can use this with an exponential number of time slots. Okay, so this idea only makes use of this hierarchy. So we can actually apply it to hierarchical identity-based Nike to get forward secure identity-based Nike. However, we don't know how to get from there to forward secure Nike because of the problem I described before, that we don't know how to build Nike from ID Nike. But we can also apply this to our new multi-authority notion and get forward secure multi-authority ID Nike. And then this last step becomes completely trivial. So we also get forward secure Nike like this. And forward secure Nike has been studied before our work. There is a work by Poncheval and Sanders that builds this based on multilinear maps. And their construction turns out to be the exact same as when you use our multilinear map-based multi-authority HID Nike and run it through this transformation. There's also another previous work that looks into building forward secure Nike from I/O. However, they need a non-standard variant of I/O that's very poorly understood, and our work is the first that builds this based on standard I/O. And finally, when you use this for our universal sampler-based construction, we get the first adaptively secure construction for an exponential number of time slots. So to summarize, I included here all the notion of IBE, PKE, and Nike that I talked about. Might look a bit intimidating, but note here on the left in the red box, you can see the IBE and PKE notion. And now in the blue box, there's the Nike notion and our new multi-authority ID Nike notion. And they are perfect mirror images of each other. So they behave exactly the same. And on the far right, there's the older ID Nike notion that has this a bit strange property that it doesn't seem to imply anything else, not even just public key encryption. Okay, so and finally I want to conclude with an interesting open problem, and that is to construct multi-authority ID Nike and maybe even the hierarchical variant from weaker assumptions, so assumptions that don't need heavy tools such as I/O or multilinear maps. And yeah, I think it's quite a challenging problem. And to solve this, I think we probably need to make progress on building hierarchical identity-based Nike from weaker assumptions first. Okay, thank you.
Thank you. Are there any questions? So these results all hold in the dishonest key generation setting? Is that right?
Yeah, that's a good point. So for a normal ID Nike, there's no distinction between honest or dishonest key generation because you only have the trusted, like the trusted central key generator, and when that is dishonest, there's no security guarantee anyway.
I see.
For our multi-authority ID Nike, it is important to consider this dishonest key registration security because now we have multiple authorities, and of course, if one of them gets corrupted or generates their key dishonestly, you don't want that the security of the other users is compromised. And yeah, so we consider this notion in our work, and we can also achieve it for all of our constructions.
But would it be easier to give construction for the honest setting?
Yes. So the way I presented them, or in particular also the non-hierarchical version is only secure in the honest key registration variant. And to achieve this dishonest variant, you need a transformation similar to this Canetti-Halevi cut, which basically uses one level of the hierarchical version to get a dishonest key registration security.
Thank you. Other questions in the meantime?
So when you construct the DKR secure Nike from your new notion, how can you get rid of the one-time signature? Is it because your new notion providing some special security properties or just some proof checks?
So the basic idea of that is that if you want to generate a shared key for a group of users in the DKR model, you first delegate your key once, and the identity you add to your actual identity is a description of the group. So for example, a hash of the identities of all users in that group. And yeah, since that key is now only useful to generate a shared key for this particular group, that's basically what gives you DKR security. And in the IBE world, you also make use of this delegation mechanism, but the thing you add is the verification key of the one-time signature. And yeah, the reason we don't need this here is that we have this group description basically that we can use instead.
Okay, thanks.
Are there any more questions? If not, let's thank Roman again. Okay, our next talk is about efficient verifiable mixed nets from lattices revisited, and the talk will be given by Antonio.
Okay. Yeah, thank you for the introduction. This is joint work with Jonathan Buttel and Vadim Lyubashevsky. Okay, so the setting is as follows. We have some set of users, they're on the left, and they have some messages that they want to publish. And we have some public board on the right, where the messages will end up being published. Now the mixnet is this group of servers in the middle that take as input the ciphertexts encrypting the messages. Will finally output all the messages. Now this privacy notion that we want to achieve, this untraceability, we want to prevent an adversary from being able to trace each message back to the particular user that sent that message. Okay. A popular application of this is electronic voting. You can think of the messages as being the votes that the users want to emit. So at the end, we want to be able to know what the users voted, but we don't want to be able to trace each vote back to the particular user that emitted that vote. Okay. Now, as for the adversarial capabilities, we assume that the adversary can observe all of the ciphertexts, also all of the plain text, as well as the communication that takes place between the different servers. The adversary is also allowed to compromise servers, and we aim to achieve this untraceability as long as one of the servers is not compromised. And similarly, the adversary can also input ciphertexts into the mixnet. Now, another security guarantee that we would like to obtain is to provide some sort of integrity. We want to avoid the servers from modifying the messages that the users wanted to input into the mixnet. Okay? So in order to do this, we upgrade the mixnets to have verifiability. That is, we have the servers providing some proof of correctness, that some cryptographic proofs that shows that they have indeed proceeded according to the specified protocol. Okay? And we will also have the users providing some proof of plaintext knowledge, among other things, to make sure that the servers don't try to decrypt malformed ciphertexts. Okay. So the first instantiation of a mixnet was given by Chaum in 1981, and it's what we call today a decryption mixnet. Now, in this setting, the servers hold a private and public keeper, and the users will encrypt their messages in a layered way, in such a way that the outermost layer corresponds to the first server in the mixnet, and the innermost layer corresponds to the last server in the mixnet. This way, the servers can take as input the list of ciphertexts. They will remove one layer of encryption and shuffle them before forwarding to the next server. So the servers proceed in this way until the last server can finally output all the shuffled plaintexts. And the idea is that as long as one of the servers keeps their shuffling permutation and their secret key hidden, then the adversary cannot trace the messages back to the particular users that send them. Okay? So that's the kind of initial construction that was proposed. Now, the main drawback of this construction is that the size of the ciphertexts increases as you add more layers to the mixnet. Okay? So that's the main issue that was solved in a follow-up instantiation of a mixnet by Park et al. And it's what we call a re-encryption mixnet. So now in this setting, the users will encrypt their messages under a single layer of encryption, and they will be using an encryption scheme that is re-randomizable. Okay? So in the context of lattice schemes, you can think of re-randomizing a ciphertext by just adding an encryption of 0. Okay? You get a different looking ciphertext, but that it still encrypts the same message. So what the servers will now do, they will take as input the ciphertexts, will re-randomize them, and shuffle them before forwarding to the following one. In this case, now the last of the servers output some list of ciphertexts, and as long as one of the servers keeps their randomness and their shuffling permutation hidden, then again you cannot trace back each of the ciphertexts back to the user that sent it. Now, for this mixnet, we require this second phase of, say, distributed decryption to be able to finally recover the messages. Okay, so those are the two kind of main realizations of a mixnet that have been proposed. Now, let's look first at the classical setting, the classical mixnet that have been constructed. And the most popular approach has been to use this second type, these re-encryption mixnets, mainly because there's these algamal ciphertexts that are quite easy to re-randomize, and there's been a lot of work to constructing these proofs of correctness, so namely for the servers to prove that their output is indeed a shuffle and re-randomization of their input. And similarly, there has been a lot of work into constructing this distributed decryption for these ciphertexts, and also with proof of correctness. Now, if we want to obtain some plausibly quantum-safe mixnet, we might want to migrate to lattice-based mixnets. There are some obvious changes we need to make. We will have to replace ciphertext by others such as Kyber, and we'll have to have our proofs rely on other assumptions such as L-level UE. And another important point that I will try to convey in this talk is that it might be more convenient to switch back to the decryption mixnet type of mixnet, especially if one wants to optimize for mixnet size. And I will go into more detail later. Okay, so there have already been a few works looking into these verifiable mixnets from lattice assumptions. And well, for the purpose of this talk, I will focus on the highlighted ones. So we have two proofs of correct shuffle and re-randomization by Costa et al. And Araña et al. These both follow a classical approach introduced by Neff, which comes down to showing inequality of polynomials. And I will describe more in detail this approach later. And then there are those two works on the right, and by Araña et al. And Huff et al. That kind of take this proof of shuffle. They rely on the proof of shuffle by Araña et al. And they well, also take care of the distributed decryption and kind of give a full implementation of a mixnet, of a re-encryption mixnet, following this framework. Now in this context, our work on one part, it identifies a soundness issue in the proof of shuffle by Araña et al. From 2021. That is also present then in the follow-up work in the mixnets. So we then propose a fix to this proof of shuffle that is, well, it's a generalization and improvement on the proof of shuffle by Costa et al. And additionally, we also, well, improve on the efficiency of the previous proposed mixnets by, again, by switching from these re-encryption mixnets to the decryption mixnet setting. So those are kind of like the two main contributions to our work. To show in some numbers, so here are the two mixnets that I had highlighted before. These are, well, the numbers without adapting the fix for the proof of shuffle, but that shouldn't produce a significant increase. And well, as you can see, the main difference is that in our work we are able to use a much smaller modulus in the lattice ring that we use, and this, well, in the end ends up coming down to smaller ciphertexts and also smaller proofs. There's the caveat that we are using a decryption mixnet, so the size naturally increases as you add more layers. So then we take the example that they suggest of having a mixnet with 4 layers, and those are the numbers that I give here, averaged per layer. I would also like to note that the numbers for the proof sizes here are given for linear size proofs. In particular, they are linear on the number of users. In the future, one would hope to be able to replace this by some zero-knowledge succinct proofs that would allow to kind of amortize for many users. And then, well, the size would still be linear, but it would be dominated by the size of the ciphertexts. Okay, but still some work to do to get those proofs. All right. So I will now describe why re-encryption mixnets might not be so suitable in the lattice setting. So as we saw at the beginning, in this type of mixnets, we require this second phase of distributed decryption to finally recover the plain texts. Now, the way this is done in lattices, well, you have your secret key that is, you have some shares of the key that you give to different parties, and these parties just compute a partial decryption of the ciphertext. And now in the lattice setting, these parties also need to add a lot of noise to this partial decryption. They have to do this noise flooding or noise drowning technique in order not to leak their secret key inside this partial decryptions. And then this leads to much larger modulus because you need to be able to withstand all this noise and still be able to decrypt. Okay, and that's what in the end leads to much larger modulus, and in the end these larger ciphertexts and proofs. There are some works looking also into how to construct distributed decryption or threshold decryption, but using only a polynomial size modulus. And well, it's still an open question whether these approaches can be adapted to the setting of the mixnets. So with this in mind, we decide instead to take a different approach, to go back to these decryption mixnets. And I will now describe our construction for a decryption mixnet. We rely on the standard lattice assumptions. We have the learning with errors problem, distinguishing between this structured version with short secrets and these other uniform samples. and another variant, which is the learning with rounding, where you have this, instead of the random noise E, you add some deterministic noise that comes from rounding. Now, for efficiency reasons, as is done, for example, in the standardized MLChem, we take these vectors and matrices with elements over this polynomial ring. Right. Now, to describe how our decryption mixnet works, we basically need to describe how we're going to do this layered encryption. Now, I said we want to rely on lattice assumptions, so kind of an obvious thing one could do is, okay, let's say we can take the INC-PA scheme that underlies Kyber. Let's take this PKE and use it to just encrypt a message in a layer way. And well, the obvious problem with this is this leads to really large ciphertexts because these schemes, well, they are not meant to be nested. And then the standard solution is just to do the so-called chem-dem composition. So looking, for example, inside the orange parenthesis, you would encrypt some secret, say K2, using your PKE, and then use this secret that's been encrypted or encapsulated. Then you would use the secret as your secret for a symmetric scheme, like AES, that then encrypts the data. Okay, and then you would be able to nest this scheme, and this now, if the symmetric scheme doesn't increase the length, then you only have a linear ciphertext expansion, namely, in each layer, you only increase by the size of the encryption of the secret. Now, since we want to make this mixnet verifiable using zero knowledge proofs, this is a bit inconvenient to prove efficiently because, well, we have this encryption scheme that lies over these polynomial rings I described, and also we have AES working on bits. We would like to have something kind of more compatible to prove. So then we decide okay, let's just replace the AES with some lattice-friendly construction, and we can just prove with a lattice proof system. Okay, so now, for example, looking at the inside the green parentheses, what we do is, okay, let's take this secret K2. Instead of using it as the key for AES, we use it as the secret that apply the learning with rounding assumption against some uniform value, and then we can mask the message with that. And well, we can improve this a bit further. We would like to decrease as much as we can the ciphertext expansion. And now here we might need some rather large KIs to be able, because we need the learning with rounding assumption to be hard over this ring where the Kyber ciphertext lives. Okay, let's say a ring with 12-bit modulus. So what we do instead is we apply the learning with rounding assumption over a much smaller modulus, say modulus 64. And then we use the value that results from this learning with rounding to decompose, to generate from them the secrets that we now apply for a level U assumption now over the larger ring. And this allows us to have a much smaller KI and also just decrease the size of the ciphertexts. So that basically describes how we do the kind of the decryption mixnet, and well, it's left to see how we can add the verifiability. Now, the core of this verifiability will be for, well, the servers need to prove that their output list is a decryption and shuffle of the original input list. And well, the core of this proof will be proving that two lists of elements are related via permutation. And that's what I will move on to describe now. Now, the classical approach that was introduced by Neff in 2001 is in the setting of finite fields. And well, the idea is if you have two lists of field elements, if they satisfy this polynomial equation, then because of the unique factorization in the field and also in the polynomial ring, you will get that the lists, that's what the equivalence relation means that they are related via permutation. Okay. Now the problem comes if one wants to adapt this approach directly to the rings used in lattice-based cryptography. And this is what is done in the work by Araña et al. From 2021. And the problem here is that these rings are not a field. These rings factor actually for all choices of modulus Q. We would like to credit Katerina Satiraki here for the observation that this approach indeed does not work over the rings used in lattice-based cryptography. Thanks to this observation, we later identified the issue in this particular proof of shuffle. And well, it's not just an issue in the proof. There's actually some simple attack that we implement and test against one of the implementations of the proof of shuffle. So in turn, we propose kind of an upgraded lemma that is now able to work over these rings that we require in lattice-based cryptography. So now we have some product of integral domains, and we need these additional ingredients. We need a subset that has such that the differences of its elements are invertible. We also need a map that maps indices from 1 to n to this set D, and it's an injective map. Okay, and now we take two lists of ring elements. Now we want to give a condition, a polynomial equality, that will imply that the messages must have been related via permutation. So this is the lemma that we introduce. Now we require this additional ingredient, is this list of elements sigma 1 through sigma n, which must lie in the special set that we have defined. And now we have a polynomial equality that instead of univariate is now based on two variables, and this additional term that we add, the one highlighted, involves this, the image of the index. So we are somehow coupling the messages to these images that lie in the special set D. The idea is that if you want to manipulate the messages, you will also have to manipulate accordingly the images of this function, but since this lies on this special set D, you will not be able to get a valid mapping on the other side. Okay, and well, this product can be seen as a generalization from the proof of shuffle by Costa et al., but since we get this generalization, we can then choose different structure for the set and the function that allows us to have a more efficient implementation. And also, well, they use this product kind of as a building block in a two-step way that mimics the classical proof by Bayer and Groth. But well, we show that we can directly use this product to prove permutation of the messages, overall getting a more efficient proof. And well, finally, to finish, it would be interesting to see how these mixed nets can be improved by using these succinct zero-knowledge proofs. Now, the scheme I have introduced is actually an INCPA scheme that also uses proofs of plaintext knowledge. And well, it would be interesting to see also, okay, you can upgrade it to have INCCA security, following, for example, the Nauer-Young paradigm. And there's the open question of whether you can construct these other types of mixed nets, the re-encryption mixed nets, using these much smaller modulus. Okay, so that's all. Thank you for your attention.
Thank you. We have time for one question.
Thank you for the talks. So regarding this proof of shuffle, wouldn't something like interpolation also work? So I mean, I know that you can't just put them in a polynomial with those roots, but you fix like a set of like fixed like distinct points, and then you build a polynomial which takes the values of like one of the lists, and you say that. Oh wait, but then no, but this will not show the. Oh no, wait, sorry, this doesn't make any sense. Okay, sorry.
That's okay.
For the re-encryption mixnet, you mentioned that you need noise flooding. Mm-hmm. Is that just because of the distributed decryption, or where do you need it?
Precisely. The distributed decryption, when you get this partial decryption of the ciphertext, if you publish it directly, this would leak information about your partial secret. So then you do the noise flooding to hide your secret key inside the, right?
Ah, okay,
yeah.
Thanks.
Thank you.
Okay, then let's thank Antonio again.
Thank you.